Mass spectrometry is a really useful technique for finding out the relative mass of something. Now that could be a single atom, or it could be anything up to a protein. We're more interested in molecules, but you could find out the relative mass of anything using mass spectrometry. And there are various different types, which you don't need to necessarily know for the AS level or the A2 level. But just to show you roughly how it works, here is a very simplified diagram of a mass spectrometer, and here is a single atom of carbon that I'm going to put through it. So the first stage is ionization. What tends to happen is beams of electrons are blasted through this part of the mass spectrometer. As your particle passes through, it becomes ionized. So I'm going to put a plus on there. Then what happens is we put it through an electromagnetic field, and it will accelerate the atom. At the point where it gets to these large magnets in a curved shape, we'll end up with its path changing due to the charge moving through a magnetic field, and it will move in a path in this direction, go through the mass spectrometer, and end up on this detector array. Now the detector array is going to send a signal to the machine which will record whereabouts on that array the atom is striking. Now we don't just send one through at a time, obviously we send lots through at a time, and what we'll get from the printout of the machine is a little graph, and it will plot the mass to charge ratio against the percentage absorption. Now the percentage of absorption is an arbitrary figure. It's basically what's the biggest mass that we could detect. We'll define that as 100. So if I was to send carbon through, almost everything that I put through will end up as the carbon-12 isotope. I'll get an enormous peak because of my carbon-12 atoms going through into there, ionized, and coming out of the detector. However, there are other isotopes. For example, if I have carbon-13, about 1.1% of carbon atoms are the carbon-13 isotope, so if I put that through my ionization field, it will as well get a positive charge. And then that will be accelerated through the particle accelerator. It will go into the magnetic field, and it will change direction in the same way as the other one did. Because this has a slightly larger mass, if you recall, F equals ma, so the magnetic field will exert a force on these particles. Because the mass is slightly larger, we're going to actually change the direction slightly less here. We will end up with the carbon-13 exiting the magnetic field at a different point, and therefore we will end up with a peak on our mass spectrum at the carbon-13 point. The detector will log this as different, and it will give us a little peak here. Whenever we're studying something organic, we usually find that we have a peak caused by the very, very common carbon-12 isotope, and then a tiny peak caused by the carbon-13 isotope, which will be right next to it, one relative mass unit up. And that translates to organic molecules. Let's have a look at ethanol. So ethanol has 2 carbon atoms, it has 6 hydrogen atoms, and it has an oxygen atom. So we are going to put our sample of ethanol into our mass spectrometer. It will go through the electron beam, and we'll end up with a positive charge at any point on the molecule. And overall here I'm going to put a positive charge. Okay, 1 electron is going to be lost, and our charged particle will be accelerated, and it will go through the mass spectrometer again, and it will come to the detector. Because this is ethanol, we have 2 carbons, 6 hydrogens and an oxygen, we will get a signal at 46 for this ethanol molecule. So 46 is what we call the molecular ion peak, sometimes abbreviated as M+. Okay, and that's 46. Now we'll also get a tiny little peak here. I haven't done that. It'll be smaller than that, but just for the camera. We'll end up with the stuff caused by the peak caused by the carbon-13, which we call an M+1 peak. That's caused by carbon-13. So that molecule will give us that readout. It's not quite that simple though, because our ethanol can actually be broken into other bits. And this happens because the energy that we're using to ionize it is actually larger than the energy that holds these atoms together, the bond enthalpy, the bond dissociation enthalpy. And because we've got more energy than is required to split these atoms apart, we can end up with all sorts of interesting fragments. So for example, if I was to break this bond here, then I would get two fragments. I would get an oxygen and hydrogen on one side, and I would get this ethyl group on the other side. Now let's say for the moment that that breaks up like this. My positive charge is now split between two things, so I've got one thing which is neutral, and actually, because we've lost an electron, it's going to have an unpaired electron there, which makes it into a radical, and we'll end up with this ion here, which is charged. You could be asked to write an equation for fragmentation, in which case you take the molecular ion, don't forget the plus charge, and you break it up into whatever fragment you're being asked for with the positive charge on that fragment, and whatever's left of the molecule is a radical with a radical dot there to show the unpaired electron. So, if we've broken our ethanol up into this, the OH group having no charge is going to collide with one of the walls of the magnet. This particle here, though, is going to go through the magnetic field, hit the direct detector array, and because it's an ethyl group, we would expect to find a peak at 29, and we do. Let's break the molecule in a different place. If we break it here, in between these two carbon atoms, we get two fragments. We get this methyl radical. So if we break up ethanol here, in between these two carbon atoms, we get this methyl radical, and this the rest of the molecule is left with the positive charge. Now again, the radical is going to go through the acceleration phase and hit the walls of the magnetic field, so it's not going to be detected. So we'll go straight through, gone. And then this one here will go round and be detected here. This time we'll get a peak at 31. The more stable the ion that we're producing, the more common it's going to be. Now you don't need to know anything more at AS and A2 than trying to work out what these fragments that are numbered on the spectrum are used for, but actually you can use fragmentation patterns to work out what functional groups are there. You can use them to work out how many carbon atoms there are. This is basically the limit that you're going to see of something, which is a little bit more powerful actually when you get into the more complicated workings of it. But let's take another example. We have this one here. We take off the hydrogen on the end. That's going to give us another peak. That will give us 45. There is no correct way in which the bonds can break. So if I take my methyl group and I put the plus on the methyl group and I put the radical on the rest of the molecule like that, actually we get one at 15. And so this is simplified. There are more which are caused by the radical interacting with other parts of the molecule. We can lose hydrogen atoms, we can lose hydrogen gas in certain circumstances. That's all more complicated than we need for A level. So, but be aware that there are other things there. Things to look for then when you're trying to work out what a certain fragment is. If we reverse the process, okay, we can see, let's look at this graph here. We can see that this is the M plus ion here, because it's the furthest one to the right, which is a reasonable size. Down here, the M plus one would be much smaller than that. We can identify those really easily because they're 1 unit away, and we end up with a tiny one and a large one. All the rest of them must be fragments. What can we say about the gaps here? Well, 46 to 45 is an obvious gap. It's a relative mass of 1. What has a relative mass of 1? Hydrogen atoms have a relative mass of 1. So therefore we've just lost an H off there. And it could be any of them in fairness. It doesn't have to be the one on the end. If we then look at 46 to 31, what we've lost there is 15. Now 15 is important because we find it here as well. And 15 is an important number because 15 is the mass of a CH3 plus, or in this case, or a CH3 radical which has disappeared. So this peak here is most likely due to the loss of 15 atomic units, or therefore a methyl group. We can do that as well if we go another 14 down. If we had a peak 14 further down, then that would be another CH2 as well. So if we had a total gap of 29, that would be a CH3 and a CH2. That would be an ethyl group working that would be missing. So in working out from the molecular ion, the M plus, to your peak, how much difference is there, and what can we learn from that? Let's take this 29 peak as well. Let's imagine we didn't know it was an ethyl. If we go from 46 down to 29, what's the difference there? It's 17. What did we know that was in the molecule? We knew it was an alcohol. What would a loss of 17 be? Well, that's a 16 and a 1, which is an oxygen and a hydrogen. We can work out what's been lost there. And that's the easiest way of working out what these fragments are.